Hello everyone, and welcome back to some more remote learning. In today's example video, we're going to go over definite integrals. Now, if you remember from the last worksheet, we learned how to estimate the area between the function and the x-axis. And really we only dealt with positive function values, so in this worksheet we're also going to talk about values where our function is negative. But remember, in that last worksheet, we were estimating. How do we find the exact value? That's by evaluating the definite integral. If you can think of those Riemann sums and then slowly making the width of our rectangle smaller and smaller, essentially making more and more subintervals, think about if you make the subintervals towards infinity. Like, for example, looking at this picture, just to give you an idea, or here I'll draw one off to the side. If we have some function that looks like, let's just do a parabola. Now remember, the more subintervals we had, the greater that in value, the more rectangles we had, the more accurate our area. So if you can envision taking in and going towards infinity, drawing so many of those smaller rectangles, that's going to be a very accurate area. So what the integral is doing is it's calculating that, but as n goes towards infinity. So getting that nice continuous area. That is the integral. And in the next video, we're going to learn exactly how to calculate that integral using the fundamental theorem of calculus. But for now, I'm going to give you different areas. So let's take a look below. Here I've pictured some function going from a to d, where I've already included the area between the function and the axis. So the area between the curve and the x-axis. So the integral from a to b is that area. That's going to be 10. You can see here's my point A to my point B. That area under the curve is labeled 10. Now if I'm going from B to C, I'm going from this point B to this point C. This is where we're going to go from the negative values of our function to our axis. So as opposed to having a positive 3, this 3, because the area is below the x-axis, is going to be a negative 3. So think about now going from A to C, integrating our function from the point A all the way to the point C. That is going to be our integral from A to B plus our integral from B to C. That's going to give us our integral from A to C, which 10 plus a negative 3, 10 minus 3 is going to be a positive 7. So this total area, 10 minus 3, is going to be 7. Now looking at from C to D, we have nicely labeled for us as 4. Now going from B to D, that's from this point B, all the way to the point D in the x, that's going to be our integral from B to C plus our integral from C to D. So adding those together, that's going to be equal to negative 3 plus a positive 4 is going to be a positive 1. So that area, negative 3 plus 4, the total area would be a positive 1. And that was again integrating from B to D. Now for number 6, we're doing that entire chunk from A to D. So that entire function pictured. We're going to add the integral from A to B plus the integral from B to C plus the integral of our function from C to D. Or we could take what we did in part 5 from B to D and add it to A to B, back up to part 1. Or we could even split it, going from A to C, and then adding our integral from C to D, which here was my integral from A to C, and then I could add that to C to D. So there's multiple ways to calculate this. Let's go ahead and just add it up. 10 minus 3 plus 4 is going to be a positive 11. You can see we'll get the same result when we add 10 plus 1, or we add 4 plus 7. a positive 11. So now that we understand that when we're below the function, that area is negative, let's move on to some properties of the definite integral. And as long as we're able to integrate f on the interval from a to b, then we'll be able to use these following properties to complete the examples I have below. So first off, what I've done is I've just labeled the integral from a to b, assuming that our integral is a to b, where a and b are both included, and we're able to integrate f along that entire interval. From a to b, we can split that at any point, going from a to some other constant that falls in that interval, and then adding that to the integral from that constant to the end of our interval. For example, let's pick some point, let's call our point c. If c falls inside this interval from a to b, drawing a quick number line, here's a, here's b. If c is somewhere in that integral, well, this formula tells us that our integral from a to c plus our integral from c to b will give us our entire integral from a to b. So let's write that out. Integrating f of x from a to c, we can then add that to our integral from c to b and get our integral from a to b. And that's again assuming that c falls within our interval from a to b. Next, think about this. If we're integrating from a to a, well, here's our number line. A is right here. If we're integrating from a to a, what's the area directly above this value? Is there an area? Do we have some width, some interval width? No, we don't. So if we're integrating from a to a, or from b to b, or from c to c, as long as those bounds are the same, this is going to be equal to 0. Next, let's take a look at going from no longer a to b, but from b to a. If we're going from b to a, that's reversing those bounds, where if b was the end of our interval, b is a greater value than a. But I can negate that and flip my bounds back to where a is my lower value and also my lower bound. I could still evaluate it this way, which you'll see in an example in the next worksheet. It's going to give me the same answer as when I negate it and go from a to b. And then lastly, this is like that constant multiple rule. We have some value c in there. We can pull that c out in front, that constant, and then multiply it by the integral from a to b of our function. So again, you can just pull that c right out in front. So if you know the integral value from a to b of f of x, well, then you'll just multiply it by c. Let's take a look at the examples now, understanding these properties. In example 1, we're going to evaluate each of the following given the graph. In part A, we're integrating our function from 0 to 4. So my point 0 to my point 4, I have an area that's below my axis, so that's going to be negative 8, and then I have an area above my axis, so that's going to be a positive 8. Negative 8 plus a positive 8 is going to be 0. Now for B, we don't even need to look at this graph because look at our bounds. From -5 to -5, that's a 0. Next, we have some constant c multiplied by f of x, and that's using the bounds from 4 to 5. So I'm going to pull my constant of 2 out in front, so I'm going to integrate f of x from 4 to 5. And I have that pictured. From 4 to 5, that's an area of 10, and it's below the axis, so that's going to be -10. 2 times -10, what's that going to give us? That's going to give us a -20. Looking at D, we're going from 2 is our lower bound and 0 is our upper bound. I want to go from 0 to 2 since I'm just given the area. Therefore, I'm going to negate my integral so that I can go from 0 to 2. I know from 0 to 2, looking at my diagram, that's an area of 8, but it's below the axis, so that's -8. And if I'm taking the opposite, because I have a negative out in front, of a -8, that's simply going to be a +8. And then lastly, part E, we're going from -5 to 5. So evaluating essentially our entire function that's pictured. Adding all those areas up, we'll add 23 to a -8, and then we'll add that to a +8 from 2 to 4, and then lastly to a -10. We can see -8 plus 8 cancels out to give us 0, and then 23 plus a -10, 23 minus 10, that's going to be 13. So my integral has a value of 13. Now for our last example on this worksheet, as opposed to having a picture, I'm just going to give you values. Integrating f of x from 0 to 7, we get a value of 10. Integrating f of x from 0 to 9, we get a value of 5. And integrating f of x from bounds 0 to 2, we get a 3. Starting off in part A, I have a -5 within my integral, so I'm going to rewrite this, pulling the -5 out in front. So this is going to be -5 times my integral of f of x dx from 0 to 2. 0 to 2 was given. Remember, 0 to 2 is 3. So this is going to be -5 times 3, which gives me a -15 in part A. Now for part B, I'm going from the bounds 7 to 9. I am not given 7 to 9. However, think about it. I'm given 0 to 7, and then I'm given 0 to 9. If I'm given this total integral and 0 to 7, I'll just be able to subtract to get the integral I want from 7 to 9. So you can see that if I was to add my integral from 0 to 7 plus my integral from 7 to 9, that would give me my integral from 0 to 9. So what I'm going to do is I'm going to take my integral from 0 to 9 and subtract my integral from 0 to 7. Essentially what I'm doing is I'm manipulating that first property we talked about, how we can break our integral up, splitting it up. All I did is I wanted a separate chunk, so I subtracted my known to get the interval that I actually wanted. And based on the given values, 0 to 9 has a value of 5, and 0 to 7 has a value of 10. 5 minus 10 is a -5. Next in part C, same concept as part B, but now I'm going from 2 to 9. I'm given 0 to 9, and I'm given 0 to 2, so if I subtract that smaller interval, I'm going to get my interval from 2 to 9, because 0 to 2 plus 2 to 9 equals 0 to 9. Zero to 9 is 5, and 0 to 2 is 3. 5 minus 3 is going to be a +2. And then now on to the last part of my example in this worksheet. I'm going from 7 to 2, and I have a 3 within my integral. What I'm going to do is I'm going to rewrite this by pulling out a 3, but also at the same time, I don't want to go from 7 to 2. I want my bounds to be from 2 to 7. So I'm also going to negate this. So pulling out that 3, then negating, I'm now going to iterate my function from 2 to 7. Going from 2 to 7, what do we have to do? We're going to have to figure out what exactly that is. I'm given 0 to 2, and I'm given from 0 to 7. So 0 to 2 plus 2 to 7 is going to give me that entire integral from 0 to 7. So this is going to be equal to -3 times my integral from 0 to 7 minus my integral from 0 to 2. leaving my -3 outside my parentheses. From 0 to 7, that was a +10, and from 0 to 2, that was a +3. 10 minus 3 is going to give me a +7, and I'm going to multiply that by -3. So -3 times 7 is equal to a -21. So -21 is my final solution on this worksheet. Think about a way to double check this. Well, we know our total integral from 0 to 9. I can take 2 to 7, add it to 0 to 2, and then finish that interval out by adding that to my integral from 7 to 9, because then I'll have from 0 to 2, that was a 3. Then from 2 to 7, I calculated that and got a +7. And then from 7 to 9, I calculated that and got a -5. So this should all sum up to be a +5. 3 plus 7 is 10, minus 5 does indeed equal +5. So this checks out. And with that last example, we wrap up this worksheet. Continue on to the next example, where we'll go further in depth with the definite integral, going over the fundamental theorem of calculus. So stay tuned and see you in the next video. But until then, good luck with your online learning.